Welcome to Module 27 of our Econometrics Series. This module focuses on modeling structural changes and regime shifts in economic time series data. Standard linear regression models, like OLS, operate under a crucial assumption. The parameters, or the betas, are constant over the entire sample period. However, economic reality is not so simple. Economies go through distinct phases or regimes, such as periods of expansion versus periods of recession. If we ignore these fundamental shifts and fit a single line through the data, as depicted by the standard linear fit poor in the graph, our model will be misspecified. This leads to biased forecasts and incorrect policy conclusions. The switching fit optimal clearly shows how a model that adapts to these structural breaks provides a much better representation of the economic variable's behavior over time. The reality gap on the right emphasizes that linear models are insufficient when economic behavior fundamentally shifts due to policy changes or external crises. We need models that can switch with the economy to accurately capture these dynamics. This decision map guides us in choosing the appropriate method for modeling structural changes. The first crucial question is whether the exact date of the structural change is known. If the date is known, simpler methods like breakpoint least squares or dummy variables are suitable. However, if the date of the regime change is unknown and must be estimated from the data itself, we must use switching regression models. Once we've opted for switching models, the next question is whether the regime change is independent over time. If it is, we use simple switching models. If the regime change is not independent, meaning the current state depends on the previous state, we then use Markov switching models. Finally, within Markov switching, we identify if the mean or the intercept of the model switches, leading to choices like switching mean or switching intercept models. In a simple switching model, the regime at any point in time is a random draw, much like rolling a pair of dice. The probability of being in a certain state, say a recession, is constant and independent of previous states. In contrast, a Markov switching model features state-dependent regimes. This means the current regime is influenced by the previous one. For example, if you are in a recession today, the probability of being in a recession tomorrow is higher due to the persistence inherent in economic cycles. This state dependence is mathematically captured by a transition matrix. Markov models are generally superior for analyzing economic data precisely because bad times, or good times, tend to persist over time, which is a common characteristic of real-world economic phenomena. The core of the switching regression model is this equation. Here, yt is our dependent variable, xt is our set of explanatory variables, and epsilon t is the error term. The key innovation is the subscript st on the coefficient vector beta, which is an unobserved state variable indicating which regime the process is in at time t. This means the coefficients beta can take on different values depending on the regime. Essentially, we are estimating two or more different models or worlds and asking the data, which world are we in right now? The model's job is to estimate the different sets of coefficients for each regime and, simultaneously, to calculate the probability that we are in a specific regime at any given point in time. First, we must specify the number of regimes, n, before estimation. This is typically set to 2 or 3, as models with many regimes become very difficult to estimate. Second, the model assumes that the errors are normally distributed. However, it is flexible enough to allow the variance of these errors to be different in each regime, which is a very useful feature. Third, the time series data is assumed to be stationary within each regime. This means we need to check our data for unit roots before estimation. A major practical challenge is that these models are highly nonlinear. The estimation process can get stuck in a local optimum, a solution that looks good but isn't the true best fit. We need to be careful to find the global optimum. Access the module directly from the standard estimate equation box. No separate add-ins are required in modern Eviews versions. This slide illustrates the specification settings for a switching regression model, typically found in econometric software like Eviews. Here, we define the core structure of our model. First, under switching type, we choose between a Markov switching model or a simple switching model, depending on whether we believe the regime transitions are state-dependent or independent. The example shows Markov is selected. Next, we specify the number of regimes. For our Hamilton GNP case study, we selected 2 regimes. A crucial decision involves identifying which regressors will have coefficients that change across regimes, regime-specific regressors, and which will remain constant, common regressors. In this example, the intercept C is specified as regime-specific, meaning its value will differ between regime 1 and regime 2. The AR1 term, however, is listed as a common regressor, implying its coefficient will be the same across both regimes. This is a critical step, as you must decide which economic relationships are expected to break or change during a crisis, becoming regime-specific, and which are expected to remain stable across all regimes. This slide focuses on an important aspect of model estimation, optimization, and setting appropriate starting values. The core problem we often encounter is that likelihood functions, especially in non-linear models like switching regressions, can have multiple peaks. If the optimization algorithm starts in the wrong place, it might converge to a false peak or a local maximum, rather than the true global maximum. This can lead to misleading or incorrect model coefficients. The solution is to increase the number of random starts for the optimization algorithm. By trying multiple starting points, the algorithm has a better chance of exploring the likelihood surface more thoroughly and finding the global maximum. As a practical troubleshooting tip, if your model yields errors or strange, counterintuitive coefficients, the first fix to consider is often increasing the number of random starting values. In Eviews, as shown on the screen, this option is typically found under the Options tab of the Model Estimation dialog. Here, we've set the number of random starts to 200, which is a common practice to enhance the robustness of your estimation. In this case study, we're going to dive into Hamilton's GNP model, a pivotal work in understanding economic cycles. Hamilton's core hypothesis was that the U.S. economy doesn't just fluctuate smoothly. Rather, it switches between distinct fast growth and slow growth phases. These shifts, he proposed, are driven by an unobserved Markov process. Our objective is to replicate his classic 1989 finding, demonstrating how U.S. business cycles can be effectively modeled as these regime switches. We'll use the GNP-Hamilton.WF1 dataset, covering post-war U.S. GNP from 1951 to 1984. For our model setup, the dependent variable will be the annualized growth rate of GNP. We're using a Markov switching method where the intercept, C, is regime-specific, allowing the average growth rate to change between phases. The autoregressive terms, AR1, AR2, AR3, and AR4, are assumed to be common, maintaining their influence across both regimes. The output confirms 2 distinct states, one where the economy grows rapidly, regime 1, and one where it contracts, regime 2. The transition matrix shows the probability of moving between states. For example, P11 is the probability of staying in regime 1, expansion, if you are already there. Similarly, P22 is the probability of staying in regime 2, recession. P12 is the probability of switching from expansion to recession. These probabilities of staying in the same state, P11 and P22, are crucial. They tell us about the stickiness or persistence of each regime. We can use these probabilities to calculate the expected duration of a regime. The formula is 1 divided by 1 minus the probability of staying in that regime. A higher probability of staying means a longer expected duration. If the estimated P22, the probability of staying in a recession, is 0.75, then the expected duration of a recession would be 1 divided by 1 minus 0.75, which equals 4 quarters, or 1 year. This provides a very useful and intuitive metric for policymakers. While the transition matrix is informative, the ultimate validation of our model comes from visualizing the results over time. The smoothed probability graph is the ultimate test. High probabilities of regime 2 should coincide with known historical economic downturns. The framework can be extended to a multivariate context using a switching VAR model. This allows us to model a system of variables like GDP, interest rates, and inflation that all switch their behavior simultaneously between regimes. A key advantage is that it allows for regime-dependent impulse response functions. This means we can analyze how a shock, like an interest rate hike, affects the economy differently in an expansion versus a recession. This is incredibly powerful for testing complex hypotheses, such as whether monetary policy is less effective during a severe economic downturn. For example, a central bank might want to know, if we raise interest rates by 1%, how much will GDP fall? A switching VAR could show that during an expansion, regime 1, GDP might fall by 0.5%, but during a recession, regime 2, the same interest rate hike could cause GDP to fall by a much larger 1.5%. This slide provides a quick reference for common Eviews commands used in switching regression analysis. For a basic, simple switching model, the command is switchreg, followed by your dependent variable y, constant c, and any autoregressive terms like AR1. To specify a Markov switching model with two regimes and a switching intercept, you use the options type equals Markov and n equals 2 within the switchreg command, along with the @c syntax to indicate that the intercept is switching. After estimation, you can view the regime probabilities graph or table using the eqname.probs command, where eqname is the name of your estimated equation. Similarly, to view the transition matrix, you use the eqname.trans command. Finally, for estimating an advanced multivariate model like a switching var, the command is switchvar. As a power user tip, while the Eviews graphical user interface is excellent for initial exploration, saving these commands in a program file is crucial. This practice ensures that your research is fully reproducible, allowing others or yourself in the future to replicate your results precisely. To summarize our discussion, first, we must identify structural change in our data. Second, we choose between a Markov